87 or 89%, something like that. If you always guess not cancerous, you actually do pretty well because of the class imbalance. She said after training, she easily got up to about 95% accuracy. So I think you should be shooting at least for that. I don't think she told me how long it took. A couple hours. Couple hours. So I think we should be good. How's it going? Any other questions or feedback? We have our crack team of TAs here to answer our questions. Go ahead.
When did you make the changes you talked about just a couple seconds ago? The fixes?
The tarball fixes?
Yeah.
No, those were done Monday.
Okay.
Yeah. Okay, any other questions? Yes?
How often should we do batch normalization and dropout, generally speaking?
You mean in your topology?
Yeah.
In your network design? Totally depends. So often people will insert multiple batch norms throughout. So they'll usually have blocks that they repeat. So like convolution relative batch norm, convolution relative batch norm, max pool, convolution. So they'll often put it in everywhere.
Okay.
Yeah.
Same with dropout.
So dropout, yeah, I mean, it just varies. I think it's not as common to have it everywhere.
Okay.
But
Dropout matters.
yeah, unfortunately. Okay, yeah, question.
I had to specifically do PI like below 4.0.0 for like otherwise it was giving me like this function does this function does.
Okay, so you had to import a specific version of the image processing library.
Yeah.
Did other people find that as well? Okay. I think we saw that on Piazza. Is that right?
I know that someone put a putting that code fixes.
Okay.
And everybody gives another error that even this doesn't exist.
Okay.
So like that is something so
It's worked out now?
yeah.
Okay, excellent.
So I'm
Please do. Thank you. Yeah.
Maybe just some quick classes. How many iterations per second is everyone getting?
How many iterations per second are you getting?
I'm getting like one iteration every 4 seconds with match.
One iteration every 4 seconds?
Yeah.
7 iterations? 7 per second?
Yeah, and I resized the 512
Yeah, so first of all, did you resize 512 by 512? You should. Okay, you definitely should. That will simplify everything. Yes.
That's too slow. You should not be training like that for a long time. So if you're kind of talking to TAs until you can get that figured out.
And it depends on your batch size too.
Yeah, right.
Yeah, so that's right. So you should resize 512 by 512 and your batch size should be small, like 2 or something, 2 or 3. Okay, good. Any other questions? Right, good. Well, let us know how it goes. Let's see. Oh, and then I think Robert did another video as part of this lab. You haven't seen it, so configure it.
Is there anything in the video that is like essential that you'd say?
Nope.
It's just additional instruction.
Right.
So if you've already sort of figured things out, you probably don't need it. So the video covers moving beyond n.sequential,
Yep.
as well as
Memory management for these Jupyter notebooks.
endoscoping stuff. Right.
And if you've never seen context managers in Python, I kind of talk about that. It's like a smattering of tips, which I think is how, if we ever do videos for these future labs, that's how it's going to be. It's just because you now have all the basics you need to be able to do this stuff on your own. Does anybody think that there's something that should be better described in the spec or in the video? Okay.
In general, for the videos, if you have stuff that's maybe not applicable to the lab itself, it could be like a different video, so like Python tips or maybe management stuff, like that would at least for like, I didn't watch this one, but like the last one, there was a lot of stuff that were good for like Python and just general tips on how to do that kind of stuff. But for like the lab itself, I had to kind of like skip all that to get to.
Somebody put timestamps that were really helpful.
Yeah.
Cool. Good note.
Also, does the data talk about how to load the data set? I think it should be pretty straightforward, but like there's like where the root is, and I was wondering if I have to mount to a drive or something, but if it's in the video, I haven't seen the whole video, so I'll just watch that then.
No.
It's just in the spec, actually.
Oh, okay.
So in the spec, it carefully goes through how to get the data set and load it and locally on your VM. Okay, great. Good. We'll keep going and let us know how it goes. I'm excited about that lab. I think it's a lot of fun. So today, we're not going to talk about final projects actually, but I'd like to talk about optimization. So throughout this class, we've talked about gradient descent, stochastic gradient descent, and I've asked you to use this optimizer called Atom. And hopefully by the end of today, we'll get to the point where we understand what Atom is and why it's currently the workhorse DNN optimizer that sort of everybody uses. This is the first thing you try. And if Atom doesn't work, then you try stochastic gradient descent. And so I want to talk about what it is, why it works, and why it's cool. And so we'll go through a little tour kind of optimization world. So this is all what's known as first order optimization. That means that we look at the loss surface, and we have some point on the loss surface, and we look at gradients, but we don't ever look at second order information like curvature or Hessians or approximate Hessians or anything like that. So these are all first order methods, meaning they rely entirely on gradients but nothing more. Okay, so there's a couple challenges to DNN optimization. We've talked about these a little bit, sort of informally. Today I'd like to make things just a little bit more formal. So we're looking for minima. There's also maxima, and then there's something called a saddle point. And a saddle point is, roughly speaking, a place where curvature in different dimensions is different. We've talked a little bit, and we'll talk a little bit more about saddle points in just a second. So this is like a little schematic of kind of what's going on and what we care about when we optimize in a deep neural net. So we have some parameter, x, or some 10 million dimensional parameter space, and we have the value of our loss function. And ideally, we'd like to get here. This is the global minimum of the surface. But we'd actually be okay if we got here, which is technically it's a local minimum, but it's really close to the global minimum in terms of its function value, the loss value. So we'd be okay if we got there. What we want to avoid is stuff like this out here, which is a local minimum, which is far away from the global minimum. So far away in terms of its loss value. And so the question is, how can we design algorithms that get us to points like these while avoiding points like those? And so just a few more concepts. So we say that a function is negatively curved if it looks something like this, has no curvature if it's flat, and positively curved if it curves like that. And technically this means that the second derivative of the function at this point is either positive or negative, or 0. And so a saddle point looks like this, where you have two input dimensions, say x1 and x2, and you have some function value, and the function, and right here in the middle, is called a saddle because in x2, the curvature is what?
Negative.
Negative. And in x1, the curvature is?
Positive.
Positive. So it looks like a little saddle. And this is a challenge for many optimization algorithms. If you ever get to a point like this, sometimes it's hard to get off of it. Okay, so with that terminology kind of in mind, let's start talking about DNN optimization algorithms. So I have this little video here. I think it will just run itself over and over and over again, but let's see here. So what this is showing, good. What this is showing is just a fictitious optimization surface. So think of this as a contour map. Sort of like a map of, like a hiking map, and there's mountains and valleys. So color represents the loss function value. Red is higher, blue is lower. So this is like a mountain over here, and this is like a mountain over here, and this is like a steep slot canyon between them, and then there's like, this is like Moab or something. You can imagine riding your bike on this, it'd be like smooth and fun. So star is the global minimum. That's where we'd like to get. And right here is where you start. And what we're plotting is we're plotting the trajectory that different algorithms take as they start here and try to get over here. So just watch this for a second and just tell me a few things that you notice. Go ahead.
Red, which is stochastic gradient descent, takes forever.
Okay, so yeah, so this one's red, and notice it's like, it's like the little engine that could. I think it will eventually get there, but not before the animation finishes.
Yeah.
Okay, what else do you notice? Yeah.
Green and pink, they get there faster, but then they overshoot it, both of them. Pink overshoots it less, but green overshoots it.
Yeah, so they kind of get there, like green has to goes over, and then it goes back. Okay, what else do you notice about green and pink? They're like,
They're all the way down.
Slippery.
yeah, they're like super aggressive. It's like turbocharged or something. They zip their way down here, realize it's the wrong direction, squiggle around and reverse course, and then head back over here and still overshoot. Okay? What else do you notice? Anything else?
Yellow looks nice.
Yellow looks, yeah. So we like yellow.
It slows down a lot right close to
Things slow down a lot when you get close to the global minimum. Why is that? Yeah, it's getting flat, and as a result, the gradients are small. Okay, so out here, there's a really strong gradient. By the way, which way does the gradient point when you're right here?
Towards the middle.
Down to the left. So that's why everybody starts off going down to the left. So interesting. So notice that the gradient does not point towards the global minimum. Right? It points in some other direction. But over time, these algorithms accumulate information and eventually sort of wind their way over there. All right, here's a few more. Here's a slightly different cost function surface. So this one looks like a bowl. Red is high, blue is low. People are starting over here. What do you notice? Oh, by the way, this is the value of the function over time. So like negative. They're trying to maximize, instead of minimize, which is the same. So what do you notice about this one?
I think we still like eta delta.
Which one do you like?
I think we still like eta delta.
Eta delta. So the yellow one?
Even though it is dancing a lot.
Okay, so quote, dancing a lot. Could you make that a little more a little more precise for us? Wiggly, okay. I think that's less precise.
It's not smooth.
Okay, not smooth. Yeah, what's going on? Like, so they don't wiggle up here, but something about these algorithms when they get down here.
Is it like a numerical stability thing?
Is it changing its step size because it's not getting anywhere?
It doesn't like that.
All blue, yellow, and black are all vibrating the same.
Yeah, so this is very interesting behavior. So some of these are very smooth. So again, green and pink overshoot, and eventually U-turn and get their way over there. Red, again, sort of gets there slowly. And these other ones do this weird jittering thing. So we're going to talk about that and try to figure out what's going on. Go ahead.
Is the jerkiness in it trying to make sure it's not stuck in some local minimum? Is it trying to correct or?
No, that is not why. None of these algorithms add noise. If there's any noise, it's maybe because of stochasticity, but here we're actually computing exact gradients. So there's no stochastic anything. I mean, it's called SGD, but it's not really. Okay, so let's just make sure we all remember this. So regular gradient descent, we have some batch, we calculate a loss, we go backwards, that gives us a gradient, and we just say, take our current weights, whatever they are, and we subtract off the gradient, and that minimizes, helps us minimize things, and we have some learning rate parameter. And different things happen as we change learning rates. Okay, so as we begin our discussion, trying to figure out and understand the behavior of these algorithms and how to improve them, I think it's useful to go over an example, which is just a simple bowl, but where it's shallow in one direction and steep in another direction. So let's look at this for a second. And I want you to tell me, if you ran gradient descent, regular gradient descent, what would the trajectory look like if we started at that reddish point, trying to get to the smiley face?
Straight up.
Okay, well, yeah, so let's start thinking. Which direction would it, so which way is the gradient pointing when we're right here?
Perpendicular to that line.
Okay, so we can ask the question, what is the gradient, what's the derivative in x and what's the derivative in y? So what is the derivative in x look like?
A little to the right.
Is it big or small?
Small.
Small. And what's the derivative in y? It's big. Okay. So which direction is it going to go if we take a step in the gradient?
Mostly in the y.
Mostly in y. Right? So it looks something like that. You got a big gradient in y, a small gradient in x. So if you take a step in the gradient direction, you'll go mostly up, but a little bit to the right. And that will put you on the other side of this bowl. And then what will happen?
Zigzag.
Look kind of the same, except backwards. So you do this over and over again, and this is what you get. So notice a couple of things. The direction that you have the farthest to travel in, meaning the x direction, is the direction that you end up taking the smallest steps in. And the direction where you don't have to travel very far, but where things are steep, you end up jittering back and forth across the edges of this canyon, of this bowl. And the result is very slow progress. So very slow progress in the x direction and jitter in the y direction. So this is symptomatic of something called ill conditioning in an optimization problem where something about your cost surface is narrow and in some directions, but it's very broad in other directions. And if you ever see jittering like this, this is symptomatic of an ill-conditioned optimization problem. So this is why some of those algorithms look like they were jittering back and forth across the bottom of the bowl. So kind of with that in mind, some people said, hey, we can improve gradient descent. And there's this family of algorithms, which I have compactly represented for you here with this regular expression. So you have rprop, irprop, irprop plus, irprop minus. Okay, and we're going to go through a couple of these variations. So the idea of rprop is it's called resilient backpropagation. And what rprop's big idea was that, you know, what you really don't want is a single learning rate for your algorithm. We just showed an example where you'd really like to move faster in x and move more slowly in y. So the big idea is let's introduce a different learning rate for each dimension. So now instead of having one learning rate, we're going to have 10 million learning rates. And we are going to try to learn what the learning rate should be as we move around in this lost surface. And the rprop rule is very simple. If the sign of the gradient flips, decrease it. If the sign of the gradient is the same, increase it. So let's talk about that for a minute. So let me explain why that rule makes sense. Yeah, here.
It seems sort of like with momentum, where like if you're doing a good thing, keep going faster. But as soon as like you did something a little bit too much, then pull back.
Okay, and so, okay, good. So if the sign of the gradient is the same, so I'm at some point in my lost surface, I calculate the gradient, and the gradient says you should go that way in x and that way in y. Okay, so we go this way in x. Forget about y for a second. And we calculate the gradient, it says go that way. You calculate the gradient, it says go that way. You calculate the gradient, it says go that way. You're like, okay, I get it. Like, feels like maybe we can go faster in that direction. But if it says calculate the y, it says go that way, take a step, and it says actually go that way. And it says go that way. It says go that way. You maybe know that what's happening is you're on one of those bowls and you're leaping over the minimum. And so you want to shrink the learning rate and try to get down to the bottom. Okay, so that's the insight from rprop. And so what's interesting about this, their specific algorithm, is that the magnitude of the update doesn't depend on the magnitude of the gradient. So what they have is let's see, I think I have, yeah, okay. So here's the specific details, and this is what I mean. So let's see if we can unpack this. So this is the change in weight, and it's just, I think this is from the paper. The change in weight IT at time t. No, I'm sorry, this is wrong. This is learning rate. This is the learning rate. So this is the learning rate adaptation rule. Is that right?
This is saying the gradient equals the positive learning rate times whatever the previous gradient was.
Yeah, okay, right. So let's look over here. So what does this say, this condition? So it's saying we need to adjust the learning rate for each weight according to these three cases. So what does this say? See if we can unpack it. So if the
gradients have the same sign.
If the gradient, so Josh says this means if the gradient